When your legs don't work like they used to before.
Good morning, everybody. Welcome. Hope everybody's doing all right this morning. How's the lighting down here? Are we about right? We have been, there's some important things to say. Exam Tuesday. It will look a lot like the homework questions that you're doing. We'll try to make the original figure and get it to you again Monday, and we'll do review Monday and a review discussion Monday at 11. So be sure to come for that. Anything else of vital importance? It will cover up through whatever this is. What is this? This is 30. So homework lesson 30 is where you'll be responsible for on Tuesday. And so look at that homework, look at the learning goals, and be ready with questions and comments on Monday. And we'll do some review to get you ready. So we have been talking about structures of molecules, and we've done a very, very simple thing. We've done what we call a Lewis dot structure. We've taken the periodic table and looked at the valence electrons, so the electrons in the outermost principal quantum level. So that would be principal quantum level 2 for the second row there. And the second row, down to row 3 of the periodic table, it's where most of the compounds that we interact with daily occur. So we're talking about S and P electrons in the outer shell, and they are interacting. If we have a group of 8, we said that was an ideal place for bonding. So we try to make groups of 8 in octets, and we looked at various ways to do that. We had ionic bonding, and in this case, we were categorizing by electronegativity. And if there's a great difference in electronegativity, if you have a very electronegative and a very electropositive element bonding together, the electron actually transfers. So it's not a sharing at all. You have one electron moves to the other atom, the other atomic center, and then it's the Coulombic attraction that holds them together. So it's the strongest possible plus-minus interaction, a full positive and a full negative charge holding them together. And we saw beautifully how that charge interaction depended on distance between the two and the relative electron affinities and ionization energies of the elements involved. So a lot of the chemistry we learned up till now helped us understand the ionic interaction. We also looked at the covalent situation. And with covalent situation, there's various flavors, but they all have shared electrons to make the bond. So perfect sharing of the electrons fulfills the octet of this chlorine molecule. And the sharing is equal. There's just beautiful symmetry. There's no electronegativity difference between, obviously, 2 chlorine atoms. But there's also most covalent bonds are polar covalent because there's a difference in electronegativity between the 2 atoms involved. And here's a classic case, HCl, hydrogen chloride, hydrochloric acid, goes by many names. But here, chlorine, much more electronegative than hydrogen. So what I've drawn here is kind of a skewed orbital, a skewed cloud of electrons favoring the chlorine side because it's more electronegative. So that actually produces something you can detect a little bit of positive, not a full positive charge. So we use this sign delta, partial positive charge here, not fully +1, but bigger than 0. And here, a partially negative charge, so not fully -1, but between 0 and 1. And that interaction enhances the strength of the bond, enhances the strength of the interaction between those, because you get this sharing interaction and the charge, the Coulombic interaction that also holds them together. So you can kind of arrange these in order of increasing bond or interaction strength. Strongly interactive, and then this intermediate case, and then the perfect covalent case. Still very strong interactions, all of them, but the ionic being the most, the strongest interaction, and this polar covalent, the most common we'll look at from here on out will be polar covalent bonds. And they occur whenever you have two unequally electronegative elements bonded together. We draw this little arrow, and that's called the dipole moment. We draw that little arrow from the positive to the negative charge. So we make it into a vector, this charge separation. And we call that the dipole moment of the molecule. It's a dipole, there's two charges. That's where the dipole comes from. And it has an orientation and it has a strength. The stronger, the more charge separation, the longer you could draw that arrow to indicate a stronger interaction, but it has directionality, and that's important. And you could detect that directionality, and we'll do that in a minute. But we've ranked these here from the lowest to the strongest interaction energy between the atoms involved. So looking more carefully at this dipole moment, this is maybe the simplest case where you just have two elements bonded together, a single bond, but every bond essentially will have some polarity to it. So that means every bond in a molecule will have some little vector contributing to the overall dipole moment of the molecule. And you can vector add them together and get the sum to get the dipole moment of the entire molecule. So here we have a perfectly symmetric arrangement of dipole moments, one pointing this way and one pointing this way. So those two would cancel each other out, and the overall dipole moment of this molecule, or this dipole interaction, would be 0. And this kind of symmetric relationship as well. So you can have bonds, all of which have dipole moments, but the molecule doesn't have a dipole moment because they cancel out. Their vector sum adds to 0. So the more symmetric the molecule is, the less likely it is to have a dipole moment. So no dipole in that kind of arrangement of dipoles, and this kind of arrangement of dipoles, though, that has a net dipole, and this, where one dipole, one charge separation is stronger than the other two, would also result in some dipole moment. And again, what we're drawing here are bonds. So there's some compound here, and there's some other compound or some other element here, and the difference in electronegativity gives you those interactions. This is the classic example right here of oxygen and two hydrogens forming water, and those dipole moments giving you a net dipole moment for water. That's okay, well, that's close enough. I stopped myself there because if this really was water, those arrows are kind of going in the wrong direction. We go from positive to negative. The oxygen would be the slightly negative end, and the hydrogen would be the slightly positive end. But same principle, doesn't matter the whole, if they were pointing the other direction, the whole dipole would just point in that direction if we had them positive or negative. So short answer is add up those dipole moments for water and you get a dipole moment for the entire molecule. So can we detect that? Well, remember almost the first day of class and a couple times since then, we've done this experiment. So if we could look at camera 4 here and the two compounds, water and hexane, we now know that the water, since the water molecule has that configuration, I'm telling you, it's bent, it has a permanent dipole moment to it, that should be some partial positive and partial negative charge involved. And that dipole should line up and it should point towards positive charges. So if it points towards positive charges and then it would move towards positive charges, interact with positive charges in that way. And so we could see that happen in the stream of water molecules. So what you have here are a lot of tiny little dipole moments in that stream. And if I take a charge and put it near that stream, I can deflect the stream. Let's see if I can deflect it more. Oh, this rod, I'll have to talk to Karen. Karen, can I have the other plastic? This one doesn't seem to hold a charge, or maybe it's just me. You can see a little of the effect, but we had it with the other kind of plastic. We got a much better deflection. And sometimes it just matters how much moisture there is in the air altogether. Charges don't tend to accumulate with. Oh man, that is just disappointing. Let's see if it makes a difference. We're also running out of water, so it has to make a difference soon. Okay, so we'll wipe some electrons off this rod. And, oh, there we go, yeah. Attract that whole stream of water towards the charged rod. But we also have this idea that a symmetric molecule, like hexanes, and they're just made of carbon and hydrogen, which don't have very big electronegativity differences. So there's no permanent dipole in this molecule, and you see no deflection at all in the hexane. So something that we looked at the first week of class, we now have a more concrete understanding of. We knew early in the first week of class, atoms were made of electrons and protons, there were charges, but what was it in the water that made the charge stand out? Didn't average to zero. This is the asymmetry of the water molecule and the permanent dipole moment that we can detect there. So what about microwaves? So how does a microwave oven work? So this brings together a lot of our quantum mechanics and our understanding of electromagnetic waves. So if you have a molecule that has a permanent dipole moment, if it interacts with electromagnetic radiation, and we know that's an oscillating electric field going up and down in strength, you could imagine a plus-minus dipole. As the wave comes in, it'll interact with one end of the molecule, and then the other end preferentially. And as the wave goes by, that molecule will just start spinning because of its dipole moment. And spinning and rocking around all over the system, and that extra molecular motion translates into, well, we know, molecules are moving more, faster, they're hotter. So a microwave oven heats up your food by mainly interacting with water molecules that have a permanent dipole moment. So you could look at these, and even now, we're not very sophisticated with our understanding of the structure of molecules, but you could say, apply this concept of transparency. If the microwaves were to interact with that water molecule and get it spinning, their energy would be absorbed. So they would transfer their energy, and they would either be fully absorbed and not even pass through, or much of the energy would be absorbed in that heating, and you'd have a dim beam of microwaves coming out the other side. So the transparency would be the wave passes right through without interacting with any of the molecules. And that's what we understand with light, too. If it were visible light, if something absorbs visible light, it removes that from the spectrum, and it's the interaction we now know of energy levels, electronic energy levels. So this is a different kind of spectroscopy. You could do microwave spectroscopy and look at the rotations of molecules and vibrations of molecules using microwaves. And it turns out, interestingly, even the rotation is quantized. The water can only rotate at certain frequencies. So which one of these would be transparent to microwaves? Let's talk about that for a minute and see what you think. There might be a little animation. Is there an animation? Yes, there's the plus minus, or the electric field varying coming in. Will it actually spin? Doesn't actually spin. Okay, talk about that amongst yourselves, and let's see if we can come to a single conclusion on that. Sorry, I'll move that so you can see it. And I think there's some, I'll put some hints up on top as well. If I could have the output of the tablet up on top. Okay, you can enter your responses, and it looks like we're doing that. B is very popular. So I think I agree with the B's. Why is that? Well, maybe we have a little animation here. What we're looking for is no permanent dipole moment. We want the microwaves to pass directly through. So we're looking for symmetry for a very symmetric looking molecule. So the most symmetric looking is this carbon dioxide molecule. These all have slightly different symmetries, and you can imagine drawing dipole moments for each bond. But here you would notice, well, those dipole moments are equal and opposite, so you'd get no total dipole moment there. But you could have little dipole moments for each of these bonds and have a total net dipole moment there and a total net dipole moment there, and you'd have an interaction with microwaves. And there's the plus-minus interaction there. I don't know what this does. Oh, look at that. It starts spinning. So that's what you expect to happen if you have a permanent dipole moment in the molecule. So this brings up another interesting point. So you know waves will interact with each other, and if you have waves and you put boundaries on them, you put them in a cavity, and a microwave oven is certainly a cavity. So you have a wave phenomena and you have boundaries, you'll get standing waves in your microwave. Certain energy standing waves in your microwave. That means that you'll have areas of high intensity of radiation and low intensity. Well, the intensity, the energy of the wave is the square of the wave. But you'll have nodes within the microwave oven where the microwave energy goes to 0. So if you have your microwave oven, oh well, we have a YouTube. Let's let this person explain it to us. Microwave's inside your oven. How do I make her go? So she's going to put cheese in the microwave oven and take out the plate, so it doesn't turn, and start it going. And there are the waves trapped in this cavity, so they add to form standing waves, and you'll have areas of high intensity, and those, when you square them, that's the microwave energy in that region, but you'll have areas where the microwave energy is high and areas where there's almost no microwave energy because there's a node in the standing wave at those places in your microwave oven. So I know many of you are like want to get up and go home right now, stopping on the way to buy some slices of American cheese so you can try this in the microwave oven. And why are so many people shaking their heads? No, that's not what I'm thinking. But you could do this, and it's even cooler than that, because what is this distance from here to here? That's the two peaks in amplitude. There's a node right between them. So this is, see if I can draw it, node, peak, node, peak. That is the microwave pattern. And you can measure the wavelength from that, can't you? You get a ruler out and measure the distance between the bubbly spots and calculate the wavelength of the microwaves in your microwave oven. And we talked about this when we talked about radiation. Microwaves, you know, they're right there next to radio waves. Microwaves have the very long wavelengths, the meters long. You get down to microwaves and they're centimeters long in wavelength. So they're about the size of a slice of cheese. And you can see that dramatically right here. So go home and do that. Mom, relax. I'm mapping the microwave. What's the best way to do that? That maybe? Nope, don't want to do that. How do I? Holy crap. Stop altogether. So let's look at this a little more carefully. We have the bonds. Each bond has a little dipole moment associated with it. That's interesting. I kind of drew them in the reverse direction here as well. Huh, must have done this before. I don't know if you guys might not have even noticed, but the oxygen is the more electronegative. So this is the little positive end, and this is the more negative end. So we've been saying, excuse me, is the more electronegative element. So electrons spend more time over on this side. A little delta negative there and a little delta positive here. So this one could have been drawn that way. It's actually interesting. Physicists do draw it. If you go to a physics class, they will draw it from negative to positive. And here in chemistry, we're drawing it from positive to negative. So it's just, it doesn't really matter. What matters is you do it consistently so you can add them up. But here, you can see I've done it opposite convention here. I have gone from positive to negative. But we see those cancel each other out, so no net dipole there. And this one has a dipole there. Very weak dipoles. Carbon and hydrogen have very similar electronegativities. So very small here, and even if so very small, the oxygen-carbon dipole wins out, and the sum, you get a slight dipole moment for that molecule too. So no dipole moment there, no interaction with microwaves. We have our word of the day here. So our word of the day . So we'll continue with our discussion of molecules. So after we've drawn this Lewis dot structure, we often realize there's more than one way to do it. And we're going to spend the next couple minutes thinking about, let's look at the different ways and decide if maybe some ways are better than other ways. When your molecule gets a little more complex, there's a lot of ways to draw the bonds. Are any of them more favorable than any other? So ozone molecule, 3 oxygens bonded together, and we can draw a Lewis dot structure that looks like this, but we could also have drawn it with the double bond over here. Those molecules compose what we call resonance structures. There's a different arrangement of single and double bonds, or different arrangement of the multiple bonds, but the overall structure of the molecule still is this bent molecule, but double bond here or double bond here, and they're equivalent. Doesn't matter which way you draw them. So the idea is that these two structures resonate back and forth. There's a resonance between them. That's not really what happens, but that's where the word comes from. The real structure is some mixture of these two. And we know that it is, if you do the spectroscopy, if you do the microwave spectroscopy, couldn't do it on this one. You wouldn't, there is no, as you know, there are no dipole moments there. Oh wait, no, they're all oxygens. There wouldn't be any dipole moments there, but if there were a dipole moment here, you could start it rotating, and you could determine if these bonds were exactly the same length or not. And you might think, well, a double bond, that would be shorter than a single bond. So you would think there'd be some kind of asymmetry if one bond was favored over the other. But it's not. These bonds are exactly identical in the molecule. So it's a perfect combination of those two, if you'd like to think of it, that it's not 2 bonds here and 1 bond here. It's 1.5 bonds there and 1.5 bonds there to make that equally symmetric molecule, equal bond strengths and bond lengths. And of course, we're going to transform in a day or two from this kind of crude balls and sticks to molecular orbitals, and we'll be able to predict, of course, that's a symmetric molecule if you look at the combinations of the atomic orbitals that make up the molecular orbitals in that case. Here's carbonate, CO3 minus, and now 3 possible places to put that double bond. Carbonate has a -2 charge, so the negative charges would also be moving around that molecule as this double bond moves around that molecule. But again, all those bonds are equivalent, and there's a -2 charge, and you could say the bond order is, you've got 3 bonding positions. You can put a bond here, here, or here, and you're going to use 1, 2, 3, 4 bonds to do that. So 4 bonds divided by 3 positions is a bond order of 1 1/3 for each one of them. Okay? Here's benzene, and now I'm using shorthand notation that you'll see in organic chemistry next semester. Every vertex here is a carbon atom. There's a carbon atom at each vertex here. And the organic chemists are lazy by nature, and they sorry, Jake. they don't even draw the hydrogens. There's also hydrogens here. So they assume you just know that. So this is a shorthand for that molecule, alternating single and double bonds there. And you could imagine the double bond being in this position or this position, these positions, and there are 6 positions to bond together, and you have those 3 extra bonds, so you get a bond order of 1.5 again there, holding that together. But the molecular orbital is beautiful and symmetric, and interestingly here, the molecular orbital spreads out over the entire molecule. So it ends up not just holding 2 atoms together, the molecular orbital holds the entire molecule together. So electron cloud is in a ring around that molecule, and that makes the molecule very stable. That all that sharing of electron density in the molecular orbital. So now we're just going to do some bookkeeping. This is not particularly exciting, but I'll go through it with you. We do it for a reason. We want to be able to, if we have a lot of different Lewis structures and we want to determine which is the better of them, we want to rank them in terms of which is the more representative of the actual structure, we need to do 2 things. Well, this is the most important one. We want to assign formal charges to the atoms in the molecule. So molecules can have charge overall, but where does that charge reside? Does it reside on an oxygen or this nitrogen or this carbon? We can do some accounting and assign charges to the individual atoms. And it's called a formal charge because it's not actually where the charge fully resides, but if you had to assign it somewhere, you'd formally assign it to one of the molecules or one of the atoms. And that helps us differentiate between what are the better Lewis structures. And you might already imagine if you're going to assign a formal charge and you're going to assign a minus formal charge, it might be a better structure if that minus formal charge ends up on the more electronegative element. That would be better than if it were on the electropositive element. So you can see it would give you a way to differentiate between various structures. So here's the Lewis dot structure for NO2 minus. So I can count up all the electrons. Nitrogen having 5 electrons in its outer shell. Oxygen having 6 electrons in its outer shell, plus 1 for the charge, 12 electrons to spread around that molecule. And here's one way to do it. And obviously the double bond could be either there or there. So there'd be resonance structures involved as well. But what we're going to do to calculate, to assign these formal charges is, let's say that the bonding is perfectly covalent. The nitrogen and oxygen can share equally, they can each count them, the bonding electrons. And again, this is just literally counting. It's just an accounting technique. So divide up the bonding pairs and say, well, this oxygen has 1, 2, 3, 4, and then of these 4, the nitrogen and oxygen are going to equally share them. So I'll give 2 to the oxygen and 2 to the nitrogen. This nitrogen has this lone pair. It gets to have those to itself. It equally shares those 4, so it gets 2 of those 4. And it equally shares those 2, so it gets 1 of those 2. And then the oxygen on the other side gets to share 1 of those, and the lone pairs it gets to itself. And you GSIs, you should watch this carefully, because this isn't normally how it's, this is unique almost to me. So if you have to go over this in discussion, look at this slide or pay extra attention to what we're doing right here. So I've divided the electrons up by sharing them, and then I count the number of them. There's 6 there, there's 5 there, there's 7 there. So that's the kind of valence electrons in the molecule. But we know the atom has valence electrons. So what are the valence electrons in the molecule? There's the distribution of the electrons among the molecules compared to the valence electrons if it were an atom. And oxygen does have 6 valence electrons. Nitrogen does have 5 valence electrons as an atom, and 6. And you notice in this case, due to your accounting here, oxygen has 1 more than it normally would have. So if it has 1 more electron than it normally would have, we'll assign the negative charge there. These 2 don't have a formal charge. This one has a formal charge of -1 because it has 1 more electron in our molecular arrangement than it did in the atomic arrangement. Okay? That puts a negative charge on that oxygen as opposed to this one, but it is resonant, so it would go back and forth. But it's also kind of pleasing that it ends up on the more electronegative element as well. Oxygen being more electronegative than nitrogen. So let's see if you can do that. How does the formal charge on nitrogen change for this process where you go from, actually let's talk through this one together and we'll do the next one after you've seen it happen once. This nitrogen to this nitrous to nitric ion. So it's formally an oxidation. Oxidation isn't mysterious. Add more oxygens, that's an oxidation. So in this oxidation reaction, how does the formal charge change between the 2 on nitrogen? Well, let's go through the procedure. You don't have to vote on it because we're just going to go through it together. So here I've drawn the two Lewis dot structures for the two molecules. We already know how the formal charge on nitrogen was here. We calculated it was 0. Can we do it for this one? Well, now nitrogen doesn't get to count those to itself because there's an oxygen there. So nitrogen gets to count half of these bonding electrons, that's 1. Half of those, that's 1 more. Half of those, that's 2 more. So now the nitrogen has 4 valence electrons in its molecular configuration, where it normally would have 5 as an atom. And that gives you a +1 for the nitrogen formal charge. So that's an increase from 0 to 1. The overall molecule, though, has a negative charge, and the formal charges do have to add up to the total charge. So is that the case? Well, we know when the oxygen looks like this, a single bond and lone pairs. We did that in the last slide, and we said, oh, well, when that happens, that one has a -1 formal charge. So we have that happening here. This one has a -1 formal charge. That one has a -1 formal charge. But now the nitrogen has a +1 formal charge, and all the formal charges add up still to the charge on the molecule. Okay, so this isn't particularly thrilling, but it is it's accounting, and it's going to help us in our next step where we're assessing the quality of our Lewis structures. Bond order in the sulfate. I thought we did this one in discussion. Sorry, I'll just talk this one through with you as well. Sulfate bond order. We're going to kind of apply this here. Here are some ways to draw the sulfate ion, SO4 - 2. So these are all more or less legitimate. You notice we're expanding the octet on sulfur, but we said we could do that when we get down into principal quantum level 3. Principal quantum level 3 brings d orbitals, d electrons can be involved, and sulfur has a greater capacity to bond because it has more available valence electrons in d, or potential for having that in the d orbitals. So these are all, you can't eliminate them just by octets. So the octets are satisfied, and we know sulfur can expand its octet. So we'd be curious, is it going to do this? Is it going to do this? Is it going to do this? By how much will sulfur expand its octet, essentially, is our question. And we're going to use, maybe that's what we do in discussion. We apply that. Well, I'm going to do it right now. Doesn't matter. In order to determine what the bond order is, 1, 1.5, or 2, in this one, it looks like the bond order is 1. I'm asking for sulfur-oxygen bond order. Well, they're all the same, and they're all a single bond. This one would have the resonance structures where these double bonds would be spread out. So you would have 1, 2, 3, 4, 5, 6 bonding pairs and 4 things to bond together. So you can use those 6 bonding pairs in 4 bonds. So you'd have 1.5 bond order. And this one, you have 2 more bonding pairs, 1, 2, 3, 4, 5, 6, 7, 8. 8 bonding pairs in 4 positions. And I don't think anybody would be surprised that that bond order is 2. Those are all double bonds. Okay? So I can do that, but the question is, what is it in sulfate? It can be 1, 1.5, or 2. Which one should I choose? Which one is the correct one? And this is where we look carefully at the formal charges, and we just apply some rules. First of all, let's try to have the minimum number of formal charges. Let's not have charges all over the place. So that's our first rule we'd like to apply. And then second, if we're going to have them, let's put the negative ones on the electronegative elements and the positive ones on the electropositive elements, if we can, as well. So keep the formal charges to a minimum, don't spread them out. Keep them as low as possible. Don't try to, if you can keep them to lower numbers, don't have formal charges growing up to 4 and 5 and 6. And then make sure they add up to the charge on the molecule. So if you apply those, this one looks horrible by that measure. Formal charges spread out all over the place. This one, not so many formal charges, but charge concentrated in here on sulfur is -2, and oxygen is more electronegative than sulfur. So having the -2 here isn't as pleasing as if it were out on the oxygens. So this one that has the formal charge out on the oxygens and kind of a minimum distribution is the one we like. And so that says that here we have a large number and distribution of charges. Don't like that one as much. Here we have a negative charge on the less electronegative element. Here, it looks like we've satisfied our general rules for formal charges. And now we can say, I had a bunch of Lewis structures that were possible, but I'm going to pick that one. And that allows me to assign a bond order to the molecule. Now on the exam, I don't generally grade you on drawing the Lewis dot structure itself, namely because it's a multiple choice and it's an online exam. You can't draw it and submit it. And it's one of those things, I know you guys never do this, but it's one of those things that every molecule out there, you can Google Lewis structure and it comes up in 2 seconds. So it's not something that I would just give you a points for doing. But I'll just ask you questions about it. So what is the best Lewis structure, and what is the bond order in the best Lewis structure? Or what is the formal charge on sulfur in the best Lewis structure? And questions like that. So you have to have the best Lewis structure in front of you. Hopefully you've just drawn it. Well, I know you guys will have all just drawn it. And then you will answer questions about formal charges and oxidation numbers and things like that. Okay, that's a power-packed discussion there of Lewis structures. Okay, let's do one more accounting technique. So we also can define oxidation numbers from Lewis structures. And again, GSIs, pay attention, because this is not the common way to do this. But it's interesting in that instead of sharing the electrons, covalently distributing them in a shared kind of distribution, you look at your Lewis dot structure and you say, well, let's not share, let's pretend it's ionic bond and give all the electrons to the more electronegative element. So we'll just do the same thing. This time we'll divide up the electrons, but say give them all to the more electronegative element. So here, oxygen gets all 8 of those and all 8 of those. So the bonds go completely to the more electronegative element, leaving the nitrogen feeling rather exposed and bare with just those 2 left over. And then you do the same thing. You compare it. So now I have a different accounting of the arrangement in the molecule. It's the ionic distribution rather than the covalent distribution of electrons. The ionic distribution of electrons gives us oxidation numbers. We do the same thing, compare it to the atoms. And we can see, well, that has too many electrons. That has too many electrons, so that looks like a negative formal charge of 2 there, and a positive oxidation number. So this is the distribution of oxidation numbers, and you can see they're quite different than formal charges. But oxidation numbers are something we're going to come to in near the last lecture in class is about oxidation numbers, and we'll see how these arise and change, and we'll look at the combustion of sugar as an oxidation, and we'll learn how the combustion of sugar in your cells is formally carried out in your mitochondria as an oxidation, and where we get the energy out of that molecule. And we get it, it's really clever, by literally transferring the electrons around from carbons to oxygens to hydrogens and harnessing that electrical energy to power your body. So let's do this one. So GSIs, you can spread out and talk about this one with everybody. We're going to look at how does the oxidation number change. And now you have, we've gone through and we've looked at the Lewis dot structure many times, so you have them in front of you. You can compare the NO2 to the NO3 and see what you think. So go ahead, talk about that for a minute. You have to scratch them out. I might just be able to, let me see if I can just put them up there. So there, can I have the output? So this is where we were doing the formal charge. So there are the two Lewis dot structures. So that'll help you look at the difference in oxidation number between those two molecules. Okay, let's see what you're thinking. Give you a chance to respond to that one. Tell me what you're thinking. Okay, let's see what the general consensus is. Many of us think it's going to increase. So, and I agree with the increases. Here they are again, the two Lewis dot structures. And you know, what we're going to do here is we're going assign all of the bonding electrons to the more electronegative element. And we looked at this one and said, well, essentially the oxygen strips away those two, and this oxygen strips away those four, and leaves poor nitrogen with just these two. And then you put another oxygen on, and now that oxygen is going to take those two as well. So you can probably say, just from that, that the oxidation number is going to increase. Here we calculated it was 3, and it looks like it's going to go up by 2 more because I'm going to lose those two. I can't count those two negative charges now either. So in the molecule, this nitrogen can count just those two. This nitrogen can't count any because the oxygens strip all of them away. And you compare that to the atom, how its valence electron shell would look in the atom, and you can see it's +3 here, and here +5. In the atom, it had 5 electrons and was neutral. Now it's missing all of them, so we assign that a +5 oxidation number. And oxidation numbers should add up to the charge on the molecule as well. So that's an increase. All right, fantastic. That's nuts and bolts stuff, so that'll happen in discussion. So we'll go to the next thing here. Now we're going to see what those bond angles actually are. We've kind of ignored exactly how they are arranged. So let's look at how they're arranged. And now we're really looking at details of the molecular structure in our roadmap of chemistry. And these are the kind of things we need to understand about that. That's what you'll be tested on. So we've drawn these Lewis dot structures. They're just sticks. And on top of that, we've drawn them all flat on a piece of paper. And molecules aren't all planar. So I think intuitively we probably all know that. So can we predict more about the structure? And this is the more useful parts of the structure, especially for you guys going into biology. It's not so much in biology, it's not so much what the atoms are or the actual bonds, it's how they're arranged. And you know, in your body you have macromolecules, and it's the macromolecular structure that drives the processes in your cell. And the complicated structures, complex structures, allow the molecule to perform functions. They allow enzymes to catalyze reactions. You're going to see at the last day of class, we said, how does your body make energy out of glucose? It's an electrically powered machine. There are giant molecules that are actually cranking like cranks because of their complex structure and churning out ATP. And it's just a gorgeous, beautiful thing. But it depends on the structure of the molecule. So how do we determine it? We know we can write Lewis dot structures. That's flat on the paper. This is trying to show you some structure where you have the this guy coming out of the plane and these two going back in away from the plane of the board. Here's the sulfate. How does that actually look in reality? How do we transfer from a Lewis dot structure to an actual geometry? One of the most important things is to define the steric number. Steric just means interaction energy. If there's a steric interaction, it's a spatial interaction. I have something here and I have to avoid it. There's a steric interaction that we have to account for. And I think it's pretty clear the steric number around sulfur here is 4. This sulfur has to account sterically in space for 4 oxygens around it. Same thing for this carbon. It has to account for 4 things around it. This oxygen also has to account for 4 things. One of them is this carbon, one of them is this hydrogen, but it also has to account for these lone pairs. They take up space. So we see a lot of steric number 4 on this molecule. We see a steric number 3 here. This oxygen has to account for that lone pair, and that sulfur. And it doesn't matter that that's a double bond. It's just what is out there, what massive nucleus out there do I have to account for? Whether I double, triple, or single bond to it, I still have to account for it taking up space out there. So what takes up space is what determines the steric number. And you can see it's the number of lone pairs and the number of bonded atoms, regardless of how they're bonded. So there's a bonded atom and 2 lone pairs. That's a steric number of 3 there. Here's steric number of 4, 2 lone pairs and 2 bonded atoms. Steric number of 4, 1, 2, 3, 4 bonded atoms. 4 there, 4 there, 4 there, 4 there, 4 there. Oops, well, we passed up the 3 one, but you get the idea. So what we say then is that those steric things out there, you try to spread them out as far as possible in space. So we do this thing called valence shell electron pair repulsion. So you put the electron pairs as far away from each other as possible because they repel each other. So VSEPR, sometimes called VESPR for the dyslexic, I guess, but valence shell electron pair repulsion says spread out everything, spread out the steric number of things as far away as possible in space. So here you have steric number 2, 2 things bonded to a central atom. That's a steric number of 2, and you know intuitively, if I have to put something here and something here, the far away spaces I can put them is 180 degrees apart from each other. That's not too surprising. If you have a steric number of 3, you also can imagine, well, the farthest I can put those from each other is 1 here. Now imagine my feet are something I got to keep away. So something at my feet, right in my chest here is the central atom. There's something out here and there's something out here. 120 degrees from each other gets them as far away from in space as possible. And I'll associate this 120 degree bond angle and this 180 degree bond angle with the steric number. So the steric number is 3. I have a trigonal arrangement and bond angles of 120. And you can keep going. I think you understand. Well, let's talk through this. Maybe you don't understand. I think you guys probably understand. We had 3 things we had to account for. We need a gymnast down here to do this next one. 1 thing there, 1 thing here, 1 thing here. Okay, I've just dismounted from the vault. And this is steric number 3. If I have to count for 1 more thing, I'm going to split my 1 thing down here into 2. And now I have to account for 4 things. And you can say, well, that is as far away as in space. I can put them from each other. And the bond angle might be 90 degrees now. But you're thinking in a plane. The molecule has 3D space. So take these 2 and put them here in space. And now I can relax from that 90 degrees down to 109 degrees and get them farther away from each other in space. I can no longer move. Okay. Let's see if we can return. nail the dismount to 3. So this interaction, tetrahedral, is what we look for. And you look at that and you say, well, wait, that doesn't look like what you just did. It does. Now we really need a gymnast. Here, 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 here. And now I have to put my hand on the floor. And if I did that, I'd have a little triangle on the floor and one hand putting straight up. That's this. Okay? The atoms are arranged at the vertices of a regular tetrahedron. The bond angle is 109 degrees. Okay? Couple more we can look at. 5, steric number 5, you have 2 bond angles now. You have a bond angle of 90 degrees and a bond angle of 120. So you have 3 equatorial and 2 axial positions. Axial means on an axis, and then equatorial around this equator region. And 6, steric number 6, they're all identical positions now again, and they're at the vertices of a regular octahedron. All the bond angles are 90, and we call that an octahedral configuration. Now again, we're at this place where I don't like it, but you have to memorize these names. I don't like it when you have to memorize things, but it's the language we're going to use. So for each steric number, you have to, this is the language we're going to use. You have to tell me what it is by using the right name. So trigonal bipyramid, octahedron, tetrahedron, triangle, line. Linear, trigonal, tetrahedral, trigonal bipyramidal. Go home and say that one a couple times. Trigonal bipyramidal and octahedral. Okay? So we're going to give the organic chemists a break. They're coming in and having exams, so we'll leave early and give them plenty of time to fill up the room. We'll see you guys on Monday. We'll review for the exam on Tuesday.